Again, welcome to everybody. As you can see by our images, barber shops are still closed in Austria. Hopefully they will open soon. So for those who are joining us for the first time, I'm essentially the salesperson, and I'm dedicated to some European regions, namely UK, Italy, Switzerland. As some of you might know, Italy is actually very active in this field, so I had the opportunity to see some of the recordings live. It's actually very difficult to make it live, especially inside 1 hour. So this will be mostly the presentation. So I will be showing you some slides, also showing you some videos as well. And perhaps by the end, if the time allows us, we can also see a couple of things in the Simulink. Perhaps we neglected a bit this, at least me in my previous presentations, but the time limit is really a serious constraint of it. So about the TMS technique itself, so that's the transmagnetic stimulation. So basically we bring one device close to the subject head. We let the current flow around this coil. That current will produce the magnetic fields, which in its turn will also produce the current induction in the brain, which is in the opposite direction to of the source. And as you know, the magnetic and the electric fields are perpendicular. So you can also see it over here on this drawing. So the electric current induced in the brain is here represented in the green. And you can actually, for this purpose, use different coils. And the most widely is basically used the butterfly one. But there is also the circular coil. This is the field, the representation of induced electric field. So as you can see, if we use this double circle or butterfly coil, then we will have much better aim at the area in the brain. Also, it's not easy to see by from this picture, but one of the restraints of the TMS technique, it is that this induced electric field doesn't penetrate too deep into the brain, so it's mostly superficial, or as we call it, related to the brain cortical. And also, as you know, the EEG is mostly sensitive to the cortical signal, so it's a quite good match. So in this case, these two techniques are limited in a pretty similar way related to the depth of or the penetration of the signal into the brain. So why would one want in first place to use the EEG recording during the TMS techniques? And perhaps to introduce you a bit also an historical perspective, I'm not sure if anybody knows when the first TMS EEG recording was attempted. It was actually in 1989. And if I come back to the second slide, so they were aiming, for instance, for the left hemisphere, and it is the Professor Krakow group. They placed a metallic, a stainless steel strip in the middle, and they just put the electrodes on the right hemisphere. But most widely, we started to see the recordings and the publications from around year 2000. And the real boom, I would say, would happen after 2010. And we can clearly distinguish two main fields, research and the clinical. Research applications are actually historically older or longer. And more recently, we have more and more clinical applications. As Christoph has said, we have the possible application in stroke. For the treatment that is now at the moment being studied by several groups, also by us. We have also, in terms of the clinical application, quite well documented and present even on the net, the treatment for depression, which use this repetitive transmagnetic stimulation, hence this small r TMS. It's basically, it's a very short TMS signal was repeated with a high frequency for a certain period of time, usually along 20-30 minutes. And it has shown benefits, and sometimes during these recordings, people want to record, during these sessions, they want to record the EEG as well to see the evolution of the recording. So if there is really tangible proof of benefit during these sessions in the EEG of the person, of the subject or patient. Also, most recently, let's say in the last 5 years, we have several attempts to combine TMS and EEG and the epilepsy field. And it seems that specifically for the genetic general epilepsy, there is a good application, since TMS can be used as a diagnostic, not only of the status itself, but also of the therapy, of the pharmacology therapy. And in terms of the research, so the first attempts were mostly in the field of motor evoked potentials, hence they are mostly present in the literature, but there are also some application in sleep research and other fields of the research. So TMS and EEG core registering is one very demanding technique. And why? It is because the artifacts. Perhaps it's not as challenging as the fMRI, but still the TMS will generate large artifacts, meaning electrical artifacts. And these, as you can see, could actually, these voltage peaks could reach 40 volts. So there is a need to avoid the amplifier saturation. If you are doing the single pulse stimulation, that it won't be that much problem. We shall see how we can solve these issues. In the repetitive transmagnetic stimulation, that is still an issue. There are also some possible mechanical artifacts, and that is due to the movement, as these magnetic fields are strong, and as we are recording the EEG, and as you know, you need metal electrodes in order to record an EEG. Then small movements of the same is possible. Hence, there are some techniques how to avoid this. There are also some physiological artifacts. It's mostly EMG due to the muscle contractions of large muscles. Those would rather induce a large artifact. And also the eye blinking or eye movement, which also will affect the EEG. Also, I'm not sure if you have ever seen, but you can find it on the internet, how does it look like the real application of the TMS. So when you press the pedal to stimulate, there is a very loud sound in terms of clicks, something like a tick, and that could have up to 100 decibels in the neighboring areas. So it's quite loud. So coming back to this first problem of the possible amplifier solution, different companies are having different solutions or proposing different solutions, and we came up with this. We called it TMS box. So it's a electrotonic box TMS, which essentially has in each channel one resistor between the input and the amplifier, and that would basically limit the possible saturation. And as the only factor now will be basically impedance between the electrode and skin, and we shall address that as well a bit later. And then here, this is a bit representation of the facial muscles. So also there are the eye muscles inside a bit. Those will produced as well, blinking and perhaps eyes rollings may occur, and depending of the position of the coil, if you're going to the posterior region, sometimes you can have activated occipital muscles, and sometimes they are difficult to avoid, but we can filtrate them. So usually with the TMS technique, some post-processing is always involved. In terms of the hardware requirements, we have the necessity of DC coupling. I have no knowledge of anybody using successfully AC amplifier of any company in any application, unless you're doing obviously after session, but then it is not the core registration. If you are looking to record evoked potentials at least 2 kilohertz, and this is absolute minimum, we recommend always higher, at least 4 kilohertz would be better. You need to have the robust circuit. We have already mentioned the voltage limiter, which in our case is a TMS box. And we also need to use the passive electrode, so we could have as short as possible the TMS artifact in the EEG. This is also used by lowering this short period of artifact is achieved by lowering the impedance. So if you would have like a 10 kilo ohms impedance, you would have probably some 5, 6 or more milliseconds artifact, which is not so good. It also depends, but for the evoked potentials, it may affect short latency evoked potentials. So which amplifiers we do recommend for this? Well, the absolute first choice would be g.HIamp, because with it you can do everything. We have also shown it has this TMS box incorporated in its solution, and you can basically record any type of the EEG and the evoked potentials during the TMS procedure. We have also and one thing to mention, it's also the amplifier with the highest count of the inputs. And in terms of the g.USBamp, some of you may have seen it in previous sessions last few days. If not, I will show it to you in a bit forward. It can be used, it's usable, but it has somewhat larger or longer latency of the artifact because it doesn't have this TMS box. And in terms of the just recording simply EEG, also our variable solution would be adequate for it. So coming back to the HIamp, coming back for the HIamp, it would be the best solution for the TMS. Excuse me. It has the possibility to record up to 256 inputs with one single amplifier, and then you would apply 4 of these boxes. But for the evoked potentials, we could actually use up to 4 of these amplifiers and have 1,000 channels. And we could perhaps use our high resolution electrodes that we have called pangolin, and thus obtain even more channels. Usually nowadays are 64 to 128 EEG channels are used, but you can also add some in this bipolar box. You can add some additional channels, so you can record, for instance, the electroechogram and the EMG. So in this case of the TMS co-registration, the EMG could be placed on the muscle that will be affected by the transmagnetic stimulation, and you would place electrodes for the electroechogram in order to clean it, to clean the EEG trace from the EOG artifacts, and those are quite naturally going to appear because these sessions usually take 10, 15, or even more minutes or even more time. If you are applying in the sleep research, then it won't be blinking present, but eyes rollings might occur. It's actually quite frequent at certain sleep stages, and especially in those that we are going to stimulate. So then you would have a possibility to easily retrieve that artifact from the EEG. It can be used for other applications as well. So it can basically record with any type of the electrodes and any type of the sensors. Also very important to mention here, it has a very high sampling rate that is important for the TMS recordings. Output is really this 38.4 kilohertz, but internally this amplifier has sample rate of 600 kilohertz, and then it's downsampled, divided by 16, so thus producing a very smooth, very precise, and easy to read EEG signal. The USB amplifier is another model as a standalone on desktop model. You can see it has a bit less channels. It has 16 inputs, but it also has 4 group of these inputs. So it's almost as you have 4 different amplifiers in one box. And it might be useful when you want to record, for instance, some different biosignals. Then you have independent ground and reference. And you can also stack up to 4 of these amplifiers, so you can reach the 64 channels also with the g.USBamp. And as the g.HIamp, it can have any type, including invasive electrodes. And then we come to our wireless device, which is, we also call it wearable EEG. So this device is weighing some 125 grams, very, very lightweight. And as you can see, it is easy to have it on hand. You wouldn't feel it, basically. It has, though, very low sample rate. So unless you're doing P300 studies, which is already a long latency evoked potentials, then you won't be able to record evoked potentials with it. It can use passive or active electrodes, and it can include some biosignals as well. As you know, each solution contains the software part as well, because hardware does nothing without it. And as you perhaps have noticed already, most of our solutions are centered around the high-speed Simulink package. It is based on the MATLAB platform and Simulink. We have chosen it because it's easier to use than the coding in the MATLAB. So it's somewhat user-friendly. It's not the simplest perhaps to use, but the simplest products also do not offer you any flexibility for the research. So this, I would say, is the best compromise between the power of the computation, the flexibility of application, and easy of the use. And perhaps by the end we shall see it briefly how how does it look like. So in this software package, we have included all our hardware. So we included all our amplifiers, but we also have some stimulating box, which we will see it by the end, can be also useful in this solution. And these devices are all identified by serial numbers. So if you have several of them in your model, then you could easily see which one is which. And also there are a lot of parameters inside of each of these amplifiers that can be adjusted. So when we double click on the amplifiers block, then we will have the overview of all those parameters and possibility to adjust them towards our needs. So we can have a tailored solution. So again, we have here a pretty basic schematic, the amplifier block. So this is the block that will simply show the connected signals on the display, and it will record it on the computer. So we have the amplifier block for the g.HIamp. You can say it is not attached. There is no HIamp attached to it because there is no serial number here indicated. And over here, this is generic name, G-scope. Over here, perhaps we can name it raw data, so we would know that we are watching the raw data and no evoked potentials. These two blocks are more used for the data conversion purposes, because the signal that comes out is not directly compatible with the MATLAB format, so we use these two blocks to adjust that. And as you see, we have a lot of blocks, and we perhaps will already address some, like a to file and from file, so we can retrieve, see the recording, and we can also save that recording. And we have seen these displays before, and you have seen the amplifier in the previous slide, but perhaps to draw your attention to the filter, more filter blocks, which are all in this light blue. So these are all different filters. Source derivation is also a sort of a filter. Then we have blocks that are related to averages and trials. Those are these orange ones. So we have baseline correction, frame blending that is also implemented in this TMS block, which we will see shortly, trigger, and so on and so on. And then we have also some analysis, online analysis blocks, which are presented in the green. And if we put a couple of these blocks more, so it's really not that big evolution, we can see parallelly the raw data and filtered ECG signal in this case, and we can see the trial or the single QRS complex in the average window here. And we can actually assign which ECG pulses will be detected and which will know, but using this threshold scope, so we can adjust with a horizontal red line, the threshold, and thus activate a specific signal. Passing to the TMS model, it's a bit more complicated, but you could still recognize few of these elements. So there is, as always, in the source, the amplifier that records the signal. Then you can perhaps recognize these displays. So these two are the average displays, and this is the raw data display. And over here we have some separation of the signal between the EEG and trigger, which are processed differently. So over here, we just take the EEG, so we could reject bad channels and perhaps filter it. And then we have the TMS processing block, which is the heart of all this application. And we can also basically transmit the recorded signal over the network. there are certain research institutions where they have their own solutions, so they want to use both. So we can transmit the data over the network via the UDP protocol, and we can also record it locally on the hard disk drive. Over here we have two displays that will actually basically count the number of the accepted trials and number of the rejected trials. So when you're performing the analysis, the recording itself, sorry, the acquisition, then if you are having only rejection counts, something is wrong and you better stop the experience and sort out that technical problem and then proceed. And once everything is fine, you will see the rising number of the acquisitions. So this is these are the parameters that are available for the TMS processing block. In this case, it is the motor one. We use very short window. This is the interval where we will basically not showing, during this period, we will not be showing any signal. Why? And that is because that large TMS artifact. And we can also adjust, if we have applied those EOG channels, EOG electrodes, then we can adjust with a display. We can read out which the ideal value for the specific subject is, and then we put that value here, and then every single blink that would be higher, its peak would be higher than this value, will be rejected. And of course, you have to adjust the sample rate. So this is there are two blocks where you need to put the sample rate, and those are the amplifier and TMS processing block. So in the beginning, I was speaking a bit about the impedance of the skin and electrode to skin connection, sorry. It is very important, and why? If we present electrically as electric schematics, the linkage between the EEG electrode, which records our brain waves, and our brain, then we could present in this way electrode to skin connection and skin itself. So as you can see, there are some capacitors present. So the higher impedance, since we have this capacitor here, then the longer time is needed for the discharge. And that is the core issue of why do we need this low impedance in the case of the TMS and in general for the TMS techniques. The electrodes that we are using, we said, are passive ones. So we have our own G.Ladybird, but you can use some from third-party providers like EasyCamp. These seem to be the most popular among the users, at least here in Europe. And then you can also, if you're recording just EEG, if you don't have a need for the evoked potential recordings, then you can use the active ones, which would need less preparation and would be easier to set up the subject for it. So in practice, in the real life, what is the workflow of the experience with the subject? First, we have to prepare the equipment and link the trigger between the TMS device and the amplifier, and it is the same regardless of which equipment it is. We have to show extra low impedances. It's never too much to remind ourselves of it. If possible, around 1 kilo ohm, or anything below 3 would be fine. Sampling rate should be high. No reference, no filters. We should use with our equipment, you should use the TMS box, which would basically inhibit the saturation of the amplifier and protect amplifier as well. You would need to route all the wires that way that they will be perpendicular to the coil. So if we have coil here above the patient, then the wires should be going like this, perpendicularly. And obviously we have to use this software TMS toolbox, so we have to prepare it. You would usually run the EEG acquisition for a while before applying TMS at all. For instance, if you have those E or G electrodes, then you would also would like to see what is the threshold for the EEG blinking of that particular subject. Also, you could you would want to verify the quality of EEG, because if EEG is bad, evoked potential will be even worse, if not unreadable. And this is the appearance of the TMS equipment. We are using this Megan Moore. A lot of companies are using it as a first choice, but essentially this technique works with any brand. I have experience with the Max team as well, with the Next team, and they all produce quite good results. There is no significant difference among them. If someone would put you the traces of the evoked potentials, 3 of them, and ask which is which equipment, which TMS, you wouldn't be able to tell. And as you remember, it is very important to connect the trigger between the amplifier. So there is the exit from the TSM equipment and input of the amplifier. So this is it's usually placed on the rear panel. Here we have our happy subject. In this case, he has the 63 electrodes plus the ground on head. And the preparation in order to lower the impedance to 1 kilo ohm takes about 30 to 40 minutes for the trained professional. You would need, if you are not that experienced, you would need probably an hour. If you are doing for the first hour, first time it will be 1 hour and a half or something of a kind. So it's also necessary to keep the impedance low, but also it's equally important to keep it low in all of the channels, because if you have half of the cap, let's say frontal channels with 1 kilo ohm, and then you have occipital and parietal electrodes with a 10 kilo ohm impedance, that would be no good either. Also, another possibility, as you can see, these are pretty thin electrodes, so they're very tiny, so you can place the coil quite close to the head, close to the brain. But there are also some other electrodes that we will be testing if we can use these ones. As you can see, they're also very, very thin, and they have a plastic cover, so you can come really close with a coil with it. So what are the requisitions, or what is important when we are considering the coil positioning? Well, we have to hit the target for sure. So if we want for person to have some motor movement, like a movement of a thumb, then we have to find the right spot on the head. We cannot just put the coil anywhere in the head and expect for person to move the thumb as it is obvious. Then we have to still keep the optimal distance to the electrodes. So we shouldn't be touching electrodes. I have found only one single instance where the electrode burned the patient's skin, and that was from the 90s. And I would say that is because of the, let's say, the electrical safety demands at the time were not so high. This was completely novel technique. Basically, the devices actually were not clinically tested for its usage. And since 2000, there are for sure no incidents of a kind. Correct angle of to the head surface, that is quite an important, as we are going to see. I will show you one publication where they exemplify it correctly, but basically it's not the same if you have if you can see my hand, let's imagine that this is coil, it's not the same to have it this way and with this angle. So 0 angle would be one result, 15 degrees will be probably different. Also, this kind of the tilting will have effect as well. And overall general, after you take care of all of this, which is not easy as you can imagine, then you have still to have the optimal orientation of entire setup in order to reduce the artifacts, which will still appear nevertheless. But we try always to minimize them. So here are a couple of illustrations of how close this coil comes to the subject head. And as you can see over here, the coil is perpendicular to the wires. You cannot see it very well here, but over here it's quite nicely visible. And how we do achieve this coil positioning? Well, definitely not just by looking at the hand. We are at the head. We are using something called neuronavigation. And for the neuronavigation, basically, we would have the MRI image, ideally from the subject, but it is not necessary. Then you would have this system, which would have some markers, some position markers on the subject or patient, him or herself. And it also has, the system also has a few markers. So basically you need 3 of them in order to have the 3D effective area covered on the coil itself. And that would actually allow the system to position the coil over the right spot. So I would perhaps play you quickly the video from the YouTube. As you can see over here, there is a subject with the electrodes over here, and you can see these markers on the patient's head. And what you did over here, if you go back, you would usually mark also the patient, the subject head. So you need the 3 points for that as well. So they bring with this pen to the nose tip, and then also they do the earlobes as well. And then you have the effectively covered the 3D space of the patient, 3D space of the coil. And that is what the gentleman was doing behind. And I have also an example for neuronavigation. So I will play you a video. Okay, I'm sorry for this. I will step a bit back. So initially, I would like to draw your attention to a few details. So over here, you can see one of the markers. Over here, you can see basically the target area. Over here is the motor cortex in front of the central sulcus. And as you can see, if we are going to do if we want for patient to move the thumb, then we have to stimulate the correct area. So if we want to stimulate abductor pollicis, then we have to actually predefine the target. And again, as you are moving, you can see these figures here. As you are moving, coil and everything else, these numbers are changing. You can basically have the target point files predefined, and you can name them whatever you like, say BCD with ABP perhaps, or with 1, 2, 3, like in this case. And then when we select it and open it, now the target area has changed, as you can see here. So it's over there. And then over here, there are some more information, but this is basically the most important one. So this is the beam target distance. That is basically the distance between the maximum of the energy induced, and that is determined by the position of the coil, and between that point and the target point itself. So ideally, this should be 0. And when it is out of range, it is in red. And as we move, it's lowering down, so we are coming close, already yellow or green. And as you can see, we are almost above the target. Sorry. So we are over here in very low figures. So the second part of the film is basically the person securing the coil with hand. And if this experience is going to take 10 minutes, as you can imagine, there will be some shifting like this. So a lot of times you may notice in these setups, the arm that secures the coil. Okay, I think I'm running out of time, so I will be going a bit faster now. Nevertheless, these are the examples of the different positions or conditions of a coils, how that will actually affect the target evoked potentials. So if we have in this blue, we have the position of the coil here, and we have the EP wave on the right-hand side, and in red we have the second position. So if the position is not correct, there will be no evoked potentials. And if you put it correctly, then we will have it. Also, another issue is the intensity, which we didn't address so far, is the intensity of the magnetic field of the stimulus itself. So as you would expect, the higher intensity, the higher the peak of the evoked potential. So over here in red, we have sorry, it's the other way around in this case, and it also depends on the electrode. So this electrode over here, by the way, is see, this looks like a P Pareto occipital third one. It is represented here. This is the frontal, left frontal and left occipital, left frontal and left occipital. And also we have example of the stimulation angle. So if we tilt a bit a coil, then we will also have a different looking evoked potentials, or no evoked potentials at all. But you can see in terms of the tilting, if you do not apply the correct orientation, then you will actually affect both latency and morphology of the evoked potentials, which are pretty important things, and that is something that you need to preserve. And also, so there are three main characteristics of every single evoked potentials, whether it is the TMS or auditory or whatever. Those are the reproducibility, those are the morphology and the latency. In this case, we can notice this patient has, or the subject has been attended one week after the first session, and it still had the same results. And over here, it's this is the divergent index they have created. So you can see if you change the stimulation site, if you do not apply the correct intensity, if you don't have correct angle, you will have basically unmeaningful results. While the repetition of the study the same day or in 1 week apart won't have, so this is the threshold, won't have any effect, thus really confirming the reproducibility of the same ones. So now, as you have just noticed, that if we have 64 channels, even if we have 16 channels, we will still need like 40 minutes for entire preparation, including narrow navigation. Thus, I have recorded some videos, sorry, that I can show you how the workflow in software does look like. So when we start the acquisition, we initially have to define where we do want to record the signal. Basically, we don't have a database, so you would need to perhaps name the directory accordingly, so you would know how to find the recording afterwards or 1 year after. And then we enter some kind of identification, either the subject name or ID, just as good. This is a training example, and the system will automatically generate this session as a TMS session. That is how we defined it. And it will give the subject ID or name. In this case, it was training. And it also include the date. In this case, this was the 22nd of March of the last year. And then when we start the model, then we will have our EEG signal here. And if we go to the acquisition mode itself, so I would like to explain you a bit. This is the filtered EEG. I'm not sure how well you can see it in the top left corner. It's written filtered EEG. And on the right-hand side, we have the window with evoked potentials. So in the plain EEG recording, we can already notice, this would be the first two frontal channels, we can notice the electrooculogram artifacts. And over here will be the first stimulus. After the first stimulus, we have already the evoked potentials. And then the second pulse with the TMS and so forth. And perhaps if I go a bit, yeah, so over here you see that we had a bit more artifacts over here. So that might happen. These are the frontal electrodes. Sometimes people do blink simultaneously with a pulse because of the sound. And we can see the progress of the evoked potential acquisition on the right-hand side. Again, we did apply the same amplitude for all of them, so you can compare. This is probably where the stimulus was produced as well, because this is the motor area, and that was indeed the case. So once we finish, we need to save the file. So we were saving. When we stop, then we will have this dialog window where we can put some, perhaps some technical notifications. We can input some information about the triggers. Let's say that subject get indisposed and we did only 39 trials out of 40. Then we can perhaps note that down, and then in the general information we can note down that subject get indisposed unrelated to the TMS technique. Then probably you would still be able to use it as a subject in the study. And when we, I fast forward it a bit. So when we open the file, then we can see those information again in the MATLAB along with the recording itself. So you can see there is a recording and there is this file that contains this metadata, as we call it. So by the end, we should get result that would somehow be similar to this. This obviously involves the post-processing because the baseline would be more like this. But over here, we have the placement of the coil. In this case, we have performed stimulation with two different intensities. One was the subthreshold that didn't produce the movement of the thumb, and the other one is the one which did, so below and above motor threshold. So red one, because it is above motor threshold, would produce the higher amplitude, obviously. And as you can see, we are managed to obtain very nice traces. How did we actually clean the artifact from the TMS? Well, the TMS actually has two components to itself. So two exponentially decaying functions that are superimposed, and the first one would be, I don't know if you have exactly over here, the first one will be the artifact that is related to the wires to the disk of the recording electrode, which contains the TMS. And then the other one, which is a very slow one, as you can see, it takes, in this case, some 15, perhaps more, it's not clear, probably 16 milliseconds of the duration. And as you remember, if we represent electrically the skin, it has this capacitor, and as this capacitor discharges, this line will be going down back to the baseline. So this is the reason why we have this line. And now you can also perhaps link the importance of the impedance and why it is necessary to have as low as possible skin impedance. If there will be the high impedance, this will be higher in amplitude and probably would take longer time. If it takes 25 milliseconds, then it will affect even more the evoked potential if it is the motor one. So basically, what we do, we post-processing, we use the post-processing to eliminate these two functions, and so we would end up with a nice clean signal like this. This is, by the way, all this is these 25 milliseconds. So if you would have a very high impedance, then your evoked potentials will be in the middle of the artifact. And if you isolate a single channel, you can see how it is clean. It is really this well defined, but that is the reason also. It is also thanks to the very high sampling rate. So we used practically 20 kilohertz here. And then we can obtain these nice results, which are very well defined. Since I'm basically running out of time, I will allow a few minutes for the questions, but I would like to give you another example. So this part here is essentially the same as we have seen so far, but there is some addition here. What we are doing basically here, there are some studies, and in certain conditions, the subject or a patient will produce a certain brain waves. So over here we have the detector of the alpha, and over here we have the display alpha waves, and over here the beta waves. And in either condition, we will actually lead this signal to our stimulator box, which will be triggered to the TMS device. So basically the patient status will trigger the transmagnetic stimulation itself. So this is what is currently have been used. It is also what is called the closed loop. So we can also see the EMG activation over here, and also a short slide about the brand compatibility. So this is the MagStim setup. As you can see, it has that arm for securing the coil, and it has a chair, so patient or subject would be as able as possible sitting immovable during those 10, 15, or 30 minutes, depending what it is. Okay, so I guess I spent a lot of time, but there is still some questions.
Thank you very much, Slobodan, for a nice presentation. Some people were asking me if we can upload the PowerPoint because it's so interesting. So we will upload the video and also the PowerPoints from Slobodan for the today webinar to the summary of day 5. So just check the conference webpage to find it.
Okay, you can also contact me by email, those of you who are interested in specific issues. So you can find me on the g.tec webpage. My name is Tanakovic again.
Sloppy, maybe you can just post your email into the chat, then people can read it.
Yes, of course.
And there's a question coming in from Barwin. What post-processing approaches do you use to clean the TMS data and remove the two artifacts that you mentioned?
So to be honest, I don't know because I'm not the developer. I know that because I was working before with the different systems, some of them were using actually the independent component analysis for that. Some are using actually the opposite phase for this slow decay from the skin capacitor.
So I can give the answer.
Yeah, perhaps
We are
Christoph knows.
estimating a linear regression model to the stimulation artifact, and then we can very efficiently remove the artifact so that it's almost not visible anymore. So after 1-2 milliseconds, you don't see the artifact anymore, and then you can process the EEG immediately afterwards. And then there's another question from Shiria. Thank you for your presentation, Dr. Slobodan. I enjoyed it. I still feel confused if we combine EEG and TMS to study the effects on TMS for research. But you mentioned that there are clinical applications. How do you see improvements of motor functions in patients via evoked potentials in this technique? Doesn't that require multiple settings?
Well, first of all, I'm not doctor. Thank you for your comments. I'm not doctor, much less physician, so I do not have, let's say, clinical expertise in this area. I mentioned the epilepsy because that is the field I was working previously in, and nevertheless, these studies are really very recent. Regarding the epilepsy.
I can give you a couple of examples. So TMS is, for example, very important for depression. And when you're treating depression with TMS, you can look at the EEG to describe what happens in the brain when you're applying the TMS. And this is, for example, very useful. Another application is for stroke rehabilitation. In this case, you can inhibit or enhance cortical function before you are running the brain-computer interface stroke rehabilitation, for example. And in this way, you can force stroke patients to use more the paretic side, or you can also force the other side of the brain to do more work, depending how you are targeting the TBS. Reng Xu, one of our postdocs, used on-demand TMS or a real-time TMS. So they were waiting for the Bereitschaftspotential of a patient. So when he was planning a certain movement, they were waiting in the EEG signal for the minimum, and then they triggered the TMS stimulation exactly in this minimum phase of the motor unit potential. So there are many different applications where you can actually combine TMS and EEG. And with that, I would like to thank you, Slobodan, very much
Thank you
for your talk. It was very interesting.